right? So this we said this is a convex optimization problem. Okay, to solve this. So what we do is this condition in equation 6, what you can see here, this we can rewrite for mathematical computational simplicity that we have. So minimization of half norm 2 of beta. So whether you minimize norm of beta or norm 2 of beta, it's one and the same. The condition will not change there, it is same. So only just for a simplification, mathematical simplification, it's convenient to express in this fashion. So minimization of half norm 2 beta with subject to the constraint that yi into xi transpose beta plus beta 0 is greater than or equal to 1, and this has to be true for all values of I from 1 to n, entire data set. Okay, for the entire training data set that we consider. So this criteria 7, if this equation 7 or the objective function what we have, so this is basically a convex optimization problem, and this requires a background of a Lagrangian primal function. I don't know whether you have come across, but for the time being we will not go into the details, but only the result part or the simplification part we will see. Okay, uh, so with that we'll continue. Okay, fine. So this is we have to understand that it is a convex optimization problem, and the solution can be obtained by using Lagrange primal function or Lagrange function what we have, okay, in terms of beta and beta 0. Now there is one more interpretation of this equation 7. So look at equation 7 here. So another way of looking at it is, uh, finding a minimum norm. This is norm 2 or norm whatever solution, such that all the data points are correctly classified. So this ensures what is the product is greater than or equal to 1 ensures. So this product is greater than or equal to 1 means all the xi's are belonging to the correct class. All the xi's are belonging to the correct class. I hope you are able to recognize that, because this term in the parenthesis what you have, this term xi transpose beta plus beta 0 would essentially represent, or it is proportional to the signed distance of the point xi to the hyperplane. And when you multiply by y, it simply indicates the distance, the true, I mean the not the sign distance, it is actual distance. So therefore it is proportional, the product is proportional to the distance of this point xi to the hyperplane. And when this is greater than or equal to 0, when this inequality conditions what you have, so this ensures that this data point xi is in the right class, I mean the correct class. Oh, that's the point. So this minimization, what I'm talking about, the minimization of norm of beta or norm 2. So finding the minimum norm solution is such that all the data points are correctly classified. So that's another way of looking at it. Okay. Also, they are at least also it is ensured that they are at least separated by a distance from the hyperplane. By that is a distance m. Okay, where m is nothing but 1 by norm of beta. So at least this is also ensured. It's not only they are separated, not only they are correctly classified, it's but also we ensure that they are m away from between the class. Okay, so any point if you take, at least they are m away from the hyperplane. Hope that's a point that you have to understand. So that's what is being said here. Uh, okay. So I said that equation 7 is a convex optimization problem. Convex optimization problem. It's a quadratic criteria, with the linear inequality constraint. So this criteria, what you have, minimization criteria, is a quadratic criteria, because norm that you have to find, right? So it's a quadratic criteria. But inequality, if you look at in equation 7, this inequality, this is a linear in x. Okay, so therefore it's a linear inequality constraint. Okay, therefore we call it as quadratic criterion with the linear inequality constraint, and that is essentially a convex optimization problem, which can be addressed by using Lagrange function, which is given here. So look at this equation 8 here. Look at the equation 8. So LP denotes the Lagrange primal function. Okay, Lagrange primal of beta, constant 1 by 2 into norm 2 of beta, minus summation I equal to 1 to n alpha I into, there is a term alpha I introduced now, it's a constant, alpha into yi into xi transpose beta plus beta 0. So this term that we already know, minus 1. Okay, so this particular term yi into xi transpose beta plus beta 0 minus 1 is essentially the same condition, the constraint that we have written in equation 7. It is the same thing, right? When you write yi into this term, minus 1 is greater than or equal to 0. That's the same term. But in order to combine this criteria, or rather constraint, with the objective function, that is minimization of the norm 2, so what we do in primal is it's combine the constants or the coefficients, alphas are used. Let us try to know what is the role of alpha here, alpha i's. For see, alpha i's, as many as alpha i's that equal to the your data points. Alpha is the number of alpha is same as the number of data points that you have, n number of data points or the training data set. So each alpha, each training data set so has a certain contribution in the minimization, of course, indirectly. Okay, uh, so this is about the Lagrangian primal function. Now Lagrangian primal function, so the objective is to minimize this now. Okay, so to minimize this, what you do is you try to derive with respect, I mean minimize with respect to beta and beta 0, beta and beta 0. Therefore we need to derive this with respect to beta, partially with respect to beta, and also partially with respect to beta 0, and equate it to 0 and get a solution. Correct? So you'll get a solution for beta and beta 0. So setting the derivatives to 0, so we have the one equation 9 here. So look at this equation 9. So this is obtained after deriving this equation 8 with respect to beta. So you understand the summation term, you have alpha I yi into xi transpose beta. That is one part that we have, right? And the other part, probably this part, that is the alpha I yi into beta 0. That's another part that you have, correct? So when you partially differentiate with respect to beta, so you will get this particular term, that is beta is equal to summation alpha I yi xi with I running from 1 to n. And similarly, if you derive with respect to beta 0, okay, so this will be only this part will remain, alpha into yi will remain, and beta 0, that's you're differentiating with respect to beta 0, and therefore so summation alpha yi is equal to 0. So we have two equations, 9 and 10, which will be helpful to solve this primal. See, always remember this primal function has a dual solution, that primal that is obtained by the dual is actually nothing but the solution of this primal by setting it to finding its minimum value or optimal value. Okay, so that's done by deriving with respect to the parameter and setting it to 0. And now substituting this values of beta, I mean equation 9 and 10 in equation 8. Okay, so if you elaborate and substitute, then you will get a solution here, which we call it as a dual. That is the Lagrangian dual function. Okay, LD it is denoted as. So this, if you look at, you need not worry about the steps now. I'll just have written the solution only here. So summation alpha I, that's equation 10 that we have here. I mean, not equation 10, that's corresponding to the first part here of the equation 8, that is norm beta 2. Okay, then after the second part over there, so can be simplified after substituting in 9 and 10 that previous equations. So you'll get half into summation. There are two summations. One is I running from 1 to n, another is k running from 1 to n. Alpha I alpha k, yi yk, xi transpose xk. Here these are all, for different values of I and k, with both I and k are running from 1 to n. So you understand that it's a xi transpose into xk is basically a inner product. It's finding an inner product of each of data points. I mean, one data point with another data point. You're finding the inner product actually. So that will elaborate at some other later point in time. So with the constraint or with subject to alpha I greater than or equal to 0. So if alpha I is is negative, then there is no point. So we consider alpha I is always greater than or equal to 0. And you understand that if alpha I equal to 0, there is no contribution here. Your alpha I equal to 0 meaning entire thing will become 0. So alpha I greater than 0 only, it has a value. Okay, it will return a value there. And this equation is called as a dual, that's what I said, dual Lagrangian function. And the solution is obtained by maximizing LD, which is similar to a convex optimization problem. Of course, it is a convex optimization problem. Now, the conditions which we wrote here in equation 9 and 10, okay, are known as KKT. That is, what is that? Yeah, Kohn-Tucker, Karush-Kohn-Tucker conditions, KKT. Okay, this I will continue further. Maybe it's a time for quiz, I believe. So please let's look at the quiz will release now.